Welcome back to another explainer. Today, we're diving into what I like to call a biostatistical detective story, right out of the medical literature. Have you ever looked at a published graph and felt like something was just kind of off? Well, today, we're exploring deceptive data visualizations, specifically what we call the error bar trap. By the end of this, you're going to be able to decode the absolute critical difference between standard deviation and standard error of the mean. Trust me, you will literally never look at a clinical data chart the same way again.
So, here's our cold open mystery for you. Why is it that some incredibly messy real-world datasets suddenly look perfectly controlled and uniform in published papers? You know exactly what I'm talking about, right? You're reading a study about a highly variable clinical trial, you know the patients are diverse, their biological responses are totally chaotic and varied, and yet, you look at the graphs, and those error bars are just unbelievably tight. It makes it look like every single patient had the exact same uniform response. But is that reality? Or is it an illusion crafted by statistical sleight of hand?
Okay, let's dive right into this. To solve this mystery, we really have to consider a core principle of continuous clinical data. Basically, evaluating this data requires separating the intrinsic variability of individual measurements from the statistical precision of a calculated estimate. When we read medical papers, we essentially have to split our brains into two entirely distinct concepts. On one hand, you have the messy, chaotic reality of individual patients. On the other hand, you have the mathematical precision of the group as a whole. Simply put, one metric tells us about the people, while the other metric tells us about our math.
All right, let's introduce our first suspect. I like to call this one the honest truth, the standard deviation, or SD. This is a descriptive statistic that quantifies the exact amount of spread or dispersion among individual data points within a single sample around its mathematical average. Think of it like this. If a researcher measures the fasting blood glucose levels of 100 adults, the standard deviation illustrates how much those individual patient values deviate from the group average. It looks right at the individuals. It essentially asks, hey, how far does John stray from the average? What about Mary? It's a direct, completely honest measure of the raw reality of your patients. And this brilliantly illustrates what that spread actually looks like in practice. Imagine zooming all the way in on your study group. That highest point right in the middle, that's your average. And the curve shows how the true patient data scatters around it. In a normal distribution, roughly 68% of your patients fall within one standard deviation of the mean. About 95% fall within two standard deviations, and 99.7% fall within three. This curve visually anchors the whole concept of individual variance. It literally shows us exactly where our actual living, breathing patients fall in that data spread. Let's see how this builds our understanding of patient populations. A large standard deviation? That tells us our patient population is highly heterogeneous. The values are scattered widely across a really broad range. That is your messy reality. On the flip side, a small standard deviation demonstrates that the individuals are tightly clustered together. But here's the absolute critical part you have to remember. Standard deviation is an inherent property of the population being studied. If an investigator recruits more patients to increase their sample size, the standard deviation doesn't just magically shrink or disappear. It simply becomes a more accurate reflection of the true, natural variance in that population. You just can't recruit your way out of a messy, diverse population.
Now let's introduce our second kinda shape-shifting suspect, the standard error of the mean, or SEM. In direct contrast to our honest truth, the standard error is an inferential statistic. It quantifies the precision of the sample average as an estimate of the true underlying population mean. We have to really zoom out now. Rather than describing individual patient variability, the standard error represents a hypothetical multiverse. It describes the variability of the sample means themselves if the entire study were to be repeated infinitely across multiple independent samples. So it doesn't tell you about the spread of your actual patients. It tells you how confident the statisticians are that their calculated average sits close to the absolute truth.
So the crucial point here is understanding this exact contrast. Looking at them side by side, we have standard deviation on one side, the spread of the patients, describing actual biological reality. On the other side, we have standard error of the mean, the uncertainty around the sample mean, describing pure statistical confidence. When you look at an SD, you're seeing the people in the trial. When you look at an SEM, you're looking at the math behind the trial. Confusing these two? Well, that's exactly how readers get completely trapped when they're analyzing data.
And here is the smoking gun of our little detective story. Mathematically, the standard error of the mean is calculated by taking the standard deviation and dividing it by the square root of the total sample size. Let's walk through why this matters so much mathematically. Because you are dividing by a number greater than 1 for literally any study with more than one participant, the SEM is mathematically guaranteed to be smaller than the SD, always. Let me repeat that, because it is absolutely vital. The standard error will always be a smaller number than the standard deviation for the exact same dataset.
Now, what's really interesting about this slide is that denominator right there, n, the total sample size. Because the denominator scales with the size of the study, the standard error of the mean will automatically decrease as the sample size increases. This mathematical relationship means that recruiting more participants directly maximizes the precision of your estimate. It drives the SEM down and narrows the margin of error. That gives clinicians greater confidence that the calculated sample average sits close to the absolute truth of the entire population. But in doing so, it also creates the perfect condition for an illusion if it's plotted on a graph.
Which brings us to the execution trap. This is super common on medical exams and unfortunately way too common in published medical manuscripts. Remember how we just proved that the SEM is always significantly smaller than the SD? Well, unscrupulous or just misguided investigators frequently capitalize on this discrepancy. Instead of plotting the standard deviation as the error bars on their graphs to show true patient variance, they deliberately plot the tiny standard error of the mean. This creates a completely false visual impression that their data is incredibly tightly controlled and possesses very low variability. They effectively hide the messy reality of their patients behind the mathematical precision of a large sample size.
So how do we actually resolve this mystery and avoid falling into the trap? We need a practical toolkit. Here is your auditor's checklist for reviewing medical papers. Rule number 1. Always, always read the figure legend. Don't just glance at the graph and assume those tiny error bars represent patient spread. Rule number 2. Actively identify the plotted metric. Ask yourself, are they showing me SD or are they showing me SEM? Remember, if it's SD, you are seeing true patient spread. If it's SEM, you might literally just be looking at a sample size effect. You, as a clinician, must ensure you do not confuse a tight standard error, which merely reflects a huge sample size, with a tight standard deviation, which reflects a truly uniform clinical response among individual patients.
Which leaves us with a final, pretty empowering question for you to ponder. Think back to the last medical paper you read, or the last graph you saw presented. Did those error bars actually reflect true clinical uniformity? Or were you just looking at the mathematical shadow of a massive sample size? Take these new critical thinking skills directly into your next journal club, and do not let the data deceive you. Thanks for joining me on this explainer. Keep questioning what you see on the page, and I'll see you next time.